Let's solve this problem involving graphing and inequalities. We'll break it down into two parts. Part A asks us to sketch the graphs of y equals 2x plus 5 and y equals the absolute value of 4x minus 3 and find their intercepts. Let's start with y equals 2x plus 5. First, let's create our coordinate axes. For y equals 2x plus 5, the y-intercept is at 0, 5, and the x-intercept is at negative 5 halves, 0. This gives us our straight line. Now for y equals absolute value of 4x minus 3. First, let's find the vertex. This occurs when 4x minus 3 equals 0, giving us x equals 3/4. The y value at this point is 0. Now we can draw our V-shaped graph. For part B, we need to solve the inequality absolute value of 4x minus 3 is less than 2x plus 5. When we have an absolute value inequality, we need to consider two cases. When 4x minus 3 is positive and when it's negative. Let's solve case 1 first. 4x minus 3 is less than 2x plus 5. Subtracting 2x from both sides gives us 2x minus 3 is less than 5. Adding 3 to both sides gives us 2x is less than 8. Therefore, x is less than 4. Now for case 2. Negative 4x plus 3 is less than 2x plus 5. Adding 4x to both sides gives us 3 is less than 6x plus 5. Subtracting 5 from both sides gives us negative 2 is less than 6x. Therefore, x is greater than negative 1/3. Combining our results, x must be greater than negative 1/3 and less than 4. We can write this in interval notation as the open interval from negative 1/3 to 4. On our graph, this represents the region where the absolute value graph is below the line. In conclusion, we've found both the graphical and algebraic solution to this problem. The graphs help us visualize where one function is less than the other, which corresponds to our algebraic solution of x being between negative 1/3 and 4. Let's solve this problem involving a perpendicular bisector. We need to find the value of k where the perpendicular bisector of a line segment passes through the point 2k. Let's start by plotting our points and creating a coordinate plane. We have the point negative 3 2/3 and the point 6 negative 7/3. Let's connect these points with a line segment. First, let's find the midpoint of this line segment. We can do this by averaging the x and y coordinates. The midpoint is 3 halves, negative 5/6. Next, we need to find the slope of our original line. The slope is negative 1/3. The perpendicular bisector will have a slope that is the negative reciprocal of this, which is 3. Using the point-slope form of a line, we can write the equation of the perpendicular bisector. We know this line passes through the point 2k, so we can substitute these coordinates into our equation. Now we can solve for k. Substituting x equals 2, k equals 3 times 2 minus 16/3, which simplifies to 2/3. Therefore, we have found that k equals 2/3. We can verify this is correct because this point lies on our perpendicular bisector, and the perpendicular bisector is equidistant from our original 2 points. Let's solve this polynomial problem step by step. We're given a polynomial p of x equals ax cubed plus bx squared plus 3x plus 2, where a and b are integers. We know that 2x plus 1 is a factor, and when divided by x plus 1, the remainder is negative 6. Let's start with the first condition. Since 2x plus 1 is a factor, if we substitute x equals negative 1/2 into p of x, it must equal 0. Let's substitute x equals negative 1/2 into our polynomial. We get a times negative 1/2 cubed plus b times negative 1/2 squared plus 3 times negative 1/2 plus 2 equals 0. Simplifying this expression, we get negative over 8 plus b over 4 minus 3 over 2 plus 2 equals 0. Multiplying everything by 8 to clear fractions, we get negative a plus 2b plus 4 equals 0. For our second condition, since the remainder is negative 6, when divided by x plus 1, p of negative 1 must equal negative 6. Substituting x equals negative 1 into our polynomial, we get negative a plus b minus 3 plus 2 equals negative 6. Simplifying, we get negative a plus b equals negative 5. Now we have a system of two equations. Negative a plus 2b plus 4 equals 0, and negative a plus b equals negative 5. Solving this system, we get that b equals 1 and it equals 6. For part B, we need to show that p of x equals 0 has only one real root. First, let's write our polynomial in factored form. Since 2x plus 1 is a factor, and we know a and b, we can factor p of x as 2x plus 1 times 3x squared minus x plus 2. To find all roots from the linear factor, we get x equals negative 1/2. For the quadratic factor, we can use the discriminate. The discriminate equals b squared minus 4ac, which is 1 minus 24, which equals negative 23. Since the discriminate is negative, the quadratic has no real roots. Therefore, p of x equals 0 has exactly one real root at x equals negative 1/2. Let's visualize this polynomial on a graph. Notice how it crosses the x-axis exactly once at x equals negative 1/2, confirming our solution. Let's solve this combination problem involving password creation and team selection. Let's start with part A. We need to form 5-character passwords from 10 available characters. We have 6 letters, A, B, C, X, Y, and Z, and 4 symbols, asterisk, $, hash, and ampersand. The important rule is that no character can be used more than once in any password. For part 1, we need to find the total number of possible passwords. Since we're selecting 5 characters from 10 available characters and order matters, we can use the combination formula multiplied by 5 factorial. That's 10 choose 5 times 5 factorial, which equals 30,240 possible passwords. For part 2, we need passwords containing at least one symbol. We can solve this using the complement method. First find passwords with no symbols, then subtract from the total. For passwords with no symbols, we select 5 letters from 6 letters. That's 6 choose 5 times 5 factorial, which is 720. Subtracting from our total gives us 29,520 passwords. For part 3, we need passwords that start with 2 letters and end with 2 symbols. Let's break this down. First, choose and arrange 2 letters from 6 letters. That's 6 choose 2 times 2 factorial, which is 30. Then choose and arrange 2 symbols from 4 symbols. That's 4 choose 2 times 2 factorial, which is 12. Finally, for the middle position, we can use any remaining character, which is 6 choices. Multiplying these together, 30 times 12 times 6 equals 2,160 passwords. For part B, we need to select a team of 8 people from 5 doctors, 4 teachers, and 6 police officers, where the number of doctors equals the number of teachers. Our strategy is to try each possible number of doctors and teachers from 0 to 4, since we can't have more than 4 of each, as there are only 4 teachers available. Let's calculate for each case, 4 x doctors and x teachers. When x equals 1, we get 20 combinations. When x equals 2, we get 900 combinations. When x equals 3, we get 600 combinations. When x equals 4, we get just 5 combinations. Adding these up gives us 1,525 possible teams. Let's solve the equation 6x caret 1/3, 2x caret minus 1/3. 1 is equal to 0. We'll use substitution to make this easier. Let's substitute y equals x caret 1/3. Then x equals y cubed, and x caret minus 1/3 equals 1/y. Substituting into the equation gives us 6y minus 2 divided by y minus 1 is equal to 0. Multiplying by y to clear the fraction, this simplifies to the quadratic equation 6, y superscript 2, y 2 is equal to 0. We can solve this using the quadratic formula. Here, a equals 6, b equals -1, and c equals -2. Plugging these values into the quadratic formula, simplifying, we get y equals 1 plus or minus 7/12, which gives us y equals 2/3 and y equals minus 1/2. Since y equals x caret 1/3, we have x equals y superscript 3. Therefore, x equals 2/3, superscript 3 equals 8/27, and x equals minus 1/2, superscript 3 equals minus 1/8. Thus, the solutions to the equation are x equals 8/27 and x equals minus 1/8. Remember to always check your solutions by substituting them back into the original equation. Let's solve this binomial expansion problem step by step. We need to find the first three terms in descending powers of x for the expression 2x squared minus 1 over 4x raised to the nth power. We're told that the expansion takes the form 256x to the 16th plus ax to the 13th plus bx to the c, where n, ab, and c are integers we need to find. Let's start by finding n. In the binomial expansion, the first term will be 2x squared to the nth power, since we're taking k equals 0. In the binomial theorem, since this needs to give us x to the 16th, we can write that 2n equals 16. Now that we know n equals 8, let's use the binomial theorem to find the first three terms. The general term in our expansion will be n choose k times 2x squared to the n minus k power times negative 1 over 4x to the k power. Let's find the first term where k equals 0. This gives us 8 choose 0 times 2x squared to the 8th power. Simplifying, we get 256x to the 16th. For the second term, where k equals 1, we get 8 choose 1 times 2x squared to the 7th power times negative 1 over 4x. After simplifying, this gives us negative 256x to the 13th. Finally, for the third term where k equals 2, we have 8 choose 2 times 2x squared to the 6th power times negative 1 over 4x squared. This simplifies to 112x to the 10th power. Therefore, we can conclude that n equals 8, equals negative 256, b equals 112, and c equals 10. And these values satisfy our original equation, giving us the first three terms of the expansion in descending powers of x. Let's solve this calculus problem step by step. We need to find the derivative of a complex fraction and show it can be written in a specific form. Here's our starting equation. We have y equals the cube root of 5x plus 2 divided by x minus 1 squared. To find dy dx, we'll need to use the quotient rule. The quotient rule states that for a fraction u over v, the derivative is v times du dx minus u times dv dx, all over v squared. Let's identify our u and v. U is the cube root of 5x plus 2, and v is x minus 1 squared. Now let's find du dx. Using the chain rule, du dx equals 1/3 times 5x plus 2 to the negative 2/3 power times 5. This simplifies to 5/3 times 5x plus 2 to the negative 2/3. Next, let's find dv dx. The derivative of x minus 1 squared is 2 times x minus 1. Now, we can substitute these into the quotient rule. Let's carefully write out v times du dx minus u times dv dx, all over v squared. This is quite messy, so let's simplify it step by step. First, let's get a common denominator in the numerator. Now, let's multiply out the terms in the numerator. 5x minus 5 minus 30x minus 12. Combining like terms in the numerator, we get negative 25x minus 17. Therefore, a equals 25 and b equals 17. And we've shown that the derivative can indeed be written in the required form. Let's solve this vector geometry problem step by step. We'll start by drawing the triangle and understanding what we're given. First, let's draw triangle OAB. We're given that vector OA is A and vector OB is B. Then there's a line XYZ that intersects the triangle at points X, Y, and Z. Let's look at the given conditions. First, OX equals 4/5 of vector B. Next, AY equals 1/3 of vector AB. Then AZ equals mu times vector A, where mu is a constant. Finally, YZ equals lambda times XY, where lambda is another constant. For part A, we need to show that XY equals 2/3, a minus 7/15 B. Let's solve this step by step. First, we know OX equals 4/5 B. For OY, we can write it as OA plus AY. Since AY is 1/3 AB, and AB is B minus A, we get OY equals 2/3 a plus 1/3 B. Now, XY equals OY minus OX. When we substitute and simplify, we get XY equals 2/3 a minus 7/15 B. For part B, we need to find YZ in terms of lambda, A, and B. Since YZ equals lambda times XY, we can simply multiply our expression for XY by lambda. For part C, we find YZ in terms of mu. YZ equals AZ minus AY. Substituting the given expressions and simplifying, we get YZ equals mu plus 1/3 a minus 1/3 B. Finally, for part D, we can find lambda and mu by equating our two expressions for yz. When we compare coefficients, we get lambda equals 5/7 and mu equals 1/7. And there we have it. We've solved for all the unknown values and verified our vector relationships. This problem showed us how to use vector algebra and ratio relationships to solve complex geometric problems. Let's solve this trigonometric equation step by step. We need to solve 3 cosecant squared of 2x over 3 minus pi over 3 equals 4, where x is between 0 and 3 pi. Let's begin by isolating the cosecant squared term. Dividing both sides by 3, we get cosecant squared of 2x over 3 minus pi over 3 equals 4/3. Next, let's recall that cosecant squared is equal to 1 over sine squared. Therefore, 1 over sine squared of 2x over 3 minus pi over 3 equals 4/3. Taking the reciprocal of both sides, we get sine squared of 2x over 3 minus pi over 3 equals 3/4. Now, let's take the square root of both sides. This gives us sine of 2x over 3 minus pi over 3 equals plus or minus the square root of 3 over 2. Let's recall the values where sine equals plus or minus square root of 3 over 2. When sine equals positive square root of 3 over 2, the angle is pi over 3 or 5 pi over 3. When sine equals negative square root of 3 over 2, the angle is 2 pi over 3 or 4 pi over 3. Therefore, 2x over 3 minus pi over 3 equals pi over 3, 2 pi over 3 for pi over 3, or 5 pi over 3. Let's solve for x in each case. For the first value, we get x equals pi. For the second value, we get x equals 3 pi over 2. For the third value, we get x equals 5 pi over 2. And for the fourth value, we get x equals 3 pi. Let's verify these solutions satisfy our domain condition of x being between 0 and 3 pi. All of our solutions, pi, 3 pi over 2, 5 pi over 2, and 3 pi, fall within this interval. Therefore, the complete solution set is x equals pi, 3 pi over 2, 5 pi over 2, and 3 pi.